Hello everyone, welcome to my English garden, and today we'll be talking about forces. So in the previous video we talked about Newton's laws of motion and we briefly discussed more or less what's a force, but here we're going to go a little bit more in detail. So, forces. Today we'll be talking about specifically four, which are weight, normal force, tension, and friction. So beginning with weight. Weight is most definitely a force, for it is the relationship between mass and acceleration, between your mass and the acceleration of gravity. So when you get on a scale, what you're really measuring is your weight, not necessarily your mass. You're being pulled by the earth at g, with the acceleration g. The reason why this happens is because there is an innate attraction between objects with mass. And so Newton discovered that this happens everywhere. So let's take this box, just sitting on a table, nothing's happening to it, but it's on Earth. It has a weight, also referred to as mg, for its mass times gravity. Weight equals mass times gravity. However, it doesn't just go straight down through the table. So there has to be a force countering it. This is what we call the normal force, which we'll draw with that squiggly end. Basically, it's the force of a surface acting on an object that is applying a force to it. It's a little confusing, but just think of it this way. The weight is pushing it down, but it just doesn't go through, so the table has to apply a force back so that it just stays there. So let's say I'm on an incline, and you put a box here. Weight will still be pointing down. However, the normal force is going to be pointing perpendicular to the surface, which is where the name normal force comes from. Normal means perpendicular in math terms. Returning to this one. Now let's say I want to pull the box completely in the positive x direction. We'll call that tension. Just tension of the rope. It's easy to remember. And assuming that the table is not frictionless, we're going to have a force of friction applied to the opposite direction. It's easy because as you pull an object in one direction, friction wants to pull it the other way. It's not going to push in your direction because if not, friction would make your thing go faster, and we know that's not the case. So these are primordially the four forces you'll learn in your physics class, at least for the first couple weeks. Forces, as we know, they're vectors. So we can have tension not necessarily going straight to the right. We can have it going at an angle. When this happens and you want to find the total force, when you're going to divide the things into x and y forces, you're going to have this as one of your x forces, this is one of your y's, this is the other one of your y's, and here you're going to have both an x and a y. So you're going to have an x1 here and you're going to have a y force there, or rather the components of the vector of force. So now, let's do an example. So let's say I have a box that weighs 500 kilograms, and I'm pulling it at an angle from the horizontal and the coefficient of friction, of kinetic friction, is mu equals 0.3. So where does this come from? Where does this mu, what is mu? Well, unlike the other forces where it's m times a, friction is going to equal mu times the normal force. Mu is the coefficient of friction, whether it's kinetic or static friction, and normal force is the normal force of the object. It depends on whether it's inclined or not, so it's important to have that in there. So you have theta equals 20 degrees. So now every time that we have a problem that deals with forces, we have to do a free body diagram, which is basically a recollection of the forces and its respective angles. So we have our box, we have weight pointing straight down, so mg, normal force pointing straight up because it's not falling down. We have tension going in this direction at 20 degrees. And we have friction pointing in the negative x direction. So now doing the sum of our forces, it's a little easier to visualize. So sum of our x forces, we have the x component of tension, which is going to be this line here. This is the adjacent line to the angle, so it's going to be t cosine 20, or just theta for now, minus friction. It's minus because it's going in the opposite direction. If this is going to be positive, this has to be negative. And that is going to equal max, because force equals ma, but this is in the x direction, so it's just going to be max. Same with the y. We have normal force plus the y component of tension minus mg. This one, however, is going to equal 0 because the box is not moving up or down. So it doesn't have a change in distance, so it doesn't have a change in velocity, so acceleration is 0. Right, so let's start solving things. So we don't really have friction, we have its coefficient, so maybe we can break this up into its meaning. So we have t cosine theta minus mu kn, stands for coefficient of kinetic friction, so it's for kinetic friction, equals max. So what we're going to find here is the acceleration at which we're pulling the box. So we want this. We have tension, or rather, I guess I didn't really give you tension, did I? So we're just going to solve this out. in terms of their variables. So we want a. We don't have n, but we have n here. So what we're going to do is we're going to solve for n and then plug it back into the x equation. So n equals mg minus t sine theta. This is done by moving these two to the other side, changing their magnitudes, their signs. And now we can plug this in for n. So you have t cosine of theta minus mu k mg minus t sine theta equals max. We just want ax, so we divide by m, and we're left with ax equals t cosine theta minus mu k mg minus t sine theta over m. Now if you want, you can start plugging in things. We don't really have t, so let's put in a value for t. Let's say it's 40 newtons. So now we have t, we have mu k, we have m, we have g. G is, of course, 9.81. T, theta, and m. We have all of those values. So now it's just a problem of plugging things in. Check out other videos on My English Garden, and I'll see you soon.